Now let's start with the problems. I did the theory of transformers. Now I want to do some problems, and afterwards maybe I'll do a few more lectures that I have passed. Didn't pass them in these 20 videos that I did with the examples and the theory, but maybe I'll do it later. I think that the basic, fundamental and important theory I have done already. So let's start with the problems. It says that we have a one-phase 4600 divided by 400. These are the voltage ratings of the transformer. 60 Hz transformer is connected to a one-phase 60 Hz 4600 volts power supply. The maximum RMS, of course. The maximum flux density in the core of the transformer is 0.85 Teslas. If the induced voltage per turn is 10 volts, determine for A the primary turns N1 and secondary turns N2, and for B the cross-sectional area AC of the core. Okay, now if we have, for A, we have to determine N1 and N2, but I'll draw the transformer, single phase, okay, and on the primary side we have some turns. On the secondary side also we have some turns. Now it says here that for one turn, only for one turn, we have 10 volts. So one turn is going to induce 10 volts in itself. But it says how many turns then we have on the primary side. So if we have 4600 volts power supply here, then the induced voltage will also be 4600 volts supplied, but in all of these turns. So all turns will have 4600 volts induced in itself. So if one turn has 10 volts, that's how the problem says. One turn has 10 volts. Then if the number of turns on the primary side will be 4600 volts divided by 10. Why? Because one has 10 volts, and if I divide 4600 volts with 10, then that is the number of volts, number of turns on the primary side, and this is 460 volts, 400 turns. So one turn has 10 volts, two turns now has 20 volts induced on the primary side, 3, 30, 4, 40, 5, 50 volts, and we have to have 460 turns on the primary side to have 4600 volts induced on the primary side. And what is the secondary turns, number of the secondary turns? Well, I hope you remember that the turns ratio is equal to N1 divided by N2, but that is also equal to the voltage V1 divided by V2. Okay, so if we have 4600 volts on the primary side, for this particular transformer we will have 460 volts on the secondary side induced voltage. So then we know that N1 is equal to, divided by N2 is equal to V1 divided by V2. Looking at this formula. So N2, number of secondary, the turns of the secondary winding is equal to V2 divided by V1 times N1. And that is equal to 460 times 460 turns divided by the induced voltage on the primary side, but that is 4600. I can cancel these two out. 46, and I get 46 turns. So the number of turns on the secondary side is 46, which is logical because a lower number of turns on the secondary side, lower voltage. That is what we have learned in this course. Let me just see if the answer is okay. I hope I didn't screw up. Yes, so it's okay. Now for B, we have to calculate what is the cross-sectional area. If you learned about magnetic circuits, I also have a course of magnetic circuits. I have done that already. I'll put this in the description. You know that the flux induced in the core, flux, is equal to the cross-sectional area of the core times the magnetic flux density. Now, what do we have what does the problem says in the what data we have? It says the maximum flux density in the core is 0.85 Teslas. But if we have the maximum value of the magnetic flux density, then we know that flux maximum is, if you have the maximum value of this is also the maximum value. You know, because this is alternating voltage. If you have alternating voltage, then the flux and the magnetic flux density also varies with time. But the core stays the same. So if you have flux maximum, then this formula holds now. So if you have the magnetic flux density, the maximum value, looking at here, 0.85 Teslas, then this is the formula for the maximum flux. But do we have the maximum flux? No, but there is one formula which I have already described or shown to you, that the induced voltage on the primary side, E1, induced EMF E1, is equal to 4.44 times N1 times flux maximum times the frequency of the system. Do you remember this formula? This is a very important formula. Now, looking at this, we have the frequency. The frequency is 60 Hertz. We have the induced voltage E1, that is 4600 volts. We have the turns on the primary side, that is equal to 460 turns. Now we can calculate what is the flux maximum in the core. Flux maximum is equal to E1 divided by 4.44 N1 times the frequency. Now let's put the values. 4600 divided by 4.44 times the number of turns, 460 times the frequency, 60. I will calculate this with my calculator. And I get that is 37.53 Webers. So it's 10 to the minus 3. This is a small value. Fluxes are generally small values. Now the AC, or the cross-sectional area, looking at this formula is equal to the maximum flux divided by the maximum magnetic flux density. The maximum flux density is 0.85. Then we get that the cross-sectional area is equal to 37.53 times 10 to the minus 3 divided by 0.85. And I get that is 44.16 times 10 to the minus 3 meters squared. This is the SI unit. So it's and that is also correct. So thank you for watching and see you in my next video. Goodbye.